The human eye is one of our most important sense organs. With it, we're able to gather an enormous amount of information about our world. Many people consider vision to be the most important of our five senses. It helps us to explore everything around us, and as a result, we learn about the color, shape, and form of the complex and beautiful world that is ours. Yet with all the information that the eye provides, it can only perceive or see a small part of the real world. There is an entire world of very small that is completely hidden from view by the unaided eye. For most of history, man was never aware of this world of the very, very small. However, since the creation of the first microscopes in the 1600s, man has attempted to build better and better instruments to discover as much as possible about this hidden world. During these past 300 years, scientists moved from single-lens magnifying glasses that can enlarge things 20 times their normal size to sophisticated ion microscopes that can enlarge objects 2 million times. This videotape will describe the history of the microscope, provide information about how microscopes work, and help you care for and use the classroom microscope for your own exploration of the world of the incredibly small. To begin with, the man given credit for viewing this invisible world for the first time was not a trained scientist. Anton van Leeuwenhoek was a Dutchman who ran a dry goods store selling cloth. He was the finest lens grinder of his time. During his life he made 247 microscopes and over 400 lenses. Lens grinding and polishing is very delicate work. The lens must be perfect, or else objects to be viewed will be blurry. People had known for hundreds of years before Leeuwenhoek that curved glass would magnify objects. Spectacles and magnifying glasses were used in the late 1200s, but these were limited in their magnifying power. Leeuwenhoek was the first person to develop a microscope powerful enough to view very tiny organisms. This is what one of his common single-lens microscopes looked like. Yet some could magnify things as much as 300 times. He used this simple microscope to look at all kinds of things. He peered at a bee's stinger, moldy bread, hair, blood, cloth fibers, the head of a fly, dust, and parts of plants. He kept careful notes and drawings of what he saw. However, his greatest discovery came when he decided to look at a drop of pond water. He saw little creatures swimming around in the water. He was the first man to see living creatures too small for our eyes to see. We now call these creatures microbes, and therefore Leeuwenhoek is known as the father of microbiology. Today, microscopes are considered one of the most important tools of science and are regularly used in chemistry, biology, medicine, agriculture, and even law enforcement. There are three kinds of microscopes: the optical, electron, and ion microscopes. The optical or light microscope is the most common kind of microscope. Light waves passing through an object or specimen are bent to form an enlarged image. There may be one or two lenses used to accomplish this. A single-lens microscope is a magnifying glass. It can be used to enlarge all kinds of objects, from small insects to the patterns of lines in your fingerprint. A magnifying glass with a power of 3 makes things appear 3 times as large. Its power is written like this 3 times. A compound microscope is made up of at least 2 lenses arranged in a tube. The objective lens is close to the specimen being viewed. It will magnify the specimen just as a magnifying glass does. A second lens, called the ocular or eyepiece, is at the other end of the microscope tube. It is nearest your eye and will magnify the image from the objective lens even more. On the nosepiece of a standard compound microscope are 3 objective lenses. Their powers are usually 4 times, 10 times, and 40 times. The eyepiece or ocular lens usually has a power of 10. Therefore, the resulting magnifications are 40 times, 100 times, and 400 times. Magnifying power is calculated by multiplying the power of the objective lens by the power of the eyepiece. Here is a compound microscope with all important parts labeled. The base supplies support for the microscope. Above the base is the stage. This is where the specimen is placed for viewing. The specimen, which is held on a glass slide, is centered over this round hole in the stage. Stage clips are used to hold the slide in place. The hole in the stage is designed to allow reflected light from the mirror beneath the stage to pass through the specimen and into the objective lens positioned above the stage. Some microscopes use an electric light under the stage instead of a mirror. Just below the stage is a disc or iris diaphragm that can be rotated to regulate the amount of light passing through the stage and specimen. The light goes through the specimen and into the objective lens where it is magnified. On the other side of the body tube is the eyepiece, which also magnifies the image. The body tube is supported above the stage by the arm. There are 2 adjustment knobs located on the arm. The coarse adjustment knob is used to lower and raise the tube rapidly. Because the nosepiece and objective lenses are attached to the tube, they will move up and down as the coarse adjustment knob is turned. The fine adjustment knob is used to move the tube slightly and focus an image even more sharply once the coarse knob has been used and adjusted. The nosepiece can be rotated so that you can select a desired magnification. When first adjusting the microscope for a new slide, always use the lowest power objective and start with the nosepiece at its lowest setting. Then turn the coarse adjustment knob upward to move the objective away from the slide until the specimen comes into focus. Improve the focus using the fine adjustment knob. By starting at the lowest setting and focusing upward, you will not have to worry about breaking the slide by lowering the objective lens into it. Once the specimen is focused, you can change directly to higher magnifications without changing the focus. However, move the nosepiece carefully so that the newly selected objective lens doesn't strike the slide. This could damage the lens and the specimen. When looking through the eyepiece, many people keep both eyes open to lessen eye strain. Here is the procedure for setting up a slide. Specimens are very thin and are either transparent or made transparent so that light can pass through them. A drop of water is placed on a clear slide. The specimen is placed in the water and a cover slip is placed over the specimen to keep the specimen in place. This entire setup is referred to as a wet or temporary mount. Sometimes it is necessary to add coloring to a specimen so that details details show up more clearly. This is called staining. Iodine or colored ink can be used as the stain. The specimen is on the slide with a cover slip in place. A drop of the stain is placed at one side of the cover slip, and a piece of towel is positioned the opposite side of the slide. The stain is drawn under the cover slip and, in the process, gives coloring to the specimen. Keep glass slides and cover slips clean. Wash them in soapy water and rinse them in clean water. When handling slides and cover slips, hold them on the edges. Avoid getting fingerprints or smudges on the glass. Here are some examples of different kinds of microscopes. This microscope is called a binocular scope because it has two eyepieces. This dissecting microscope is used to examine larger three-dimensional specimens that aren't transparent. Optical or light microscopes can magnify things up to about 2,000 times. Electron microscopes don't use light, but instead a beam of electrons is used to magnify objects. This gives the electron microscope the ability to magnify things up to 1,000,000 times. Yet the most powerful microscope is called the ion or ion field microscope. It can magnify objects up to 2,000,000 times. The electron and ion microscopes have helped scientists observe the structure of objects as small as bacteria or viruses. Even individual atoms of thorium and uranium have been photographed by these powerful microscopes. An incredible world of shape and form unfolds under the electron and ion microscopes. Their pictures are not in color because they don't use light, and white light, of course, contains all the colors. You don't need fancy electron microscopes to experience the joy of discovery. A compound microscope can open the door to this world of the very, very small.